Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we are continuing with partial differentiation, looking at stationary points for multivariable functions. So if you're ready to learn, then let's get into it. In a previous video, we've looked at stationary points for functions of one variable. But what happens for functions of two independent variables? Well, there's three stationary points. One is this local maximum, which you can see we have this maximum red point at the top. We have these disks, which are our contour lines, and when we look from the bird's eye view, we can see it's getting up and up. There'd be like a hill on a map, and these are the contour lines of the height of the hill. And the value of the function u of x and y will decrease away from this point, so the value is going down in all directions. Then there's a minimum, which is this red point at the bottom of our function. Again, we have our contour lines, and this would be like a dip or a valley in the map, and this is at the bottom of the valley, and so any point away from this is going to be increasing in value of u. And then finally, we have the saddle point, which, as you can see, this looks like a saddle of a horse, and in one direction, going up this side of the function, you can see I'd be like this way. We're increasing the value of u, but going off the side of it, we're having decrease in value, so these directions. Therefore, it's a saddle point because it can increase or decrease depending on the direction that we take. So stationary points are located where our total differential du is equal to 0 locally. So this leads to simultaneous equations, which is partial du by dx equals 0 and partial du by dy equals 0. This leads to several points x0, y0, which satisfy this condition. And this would be the equivalent of before when we had just dy by dx equaling 0. That tells us the gradient is 0, therefore we have a stationary point. And then we'd use d2y by dx squared to find what is the form of this stationary point. Is it equal to 0? Is it greater than 0? Is it less than 0? And that would tell us what type of stationary point it is. Here, though, we're going to be using something called the character, and this is represented by E0. So this is the character of our stationary point, and it's equal to partial d2u by dx dy squared minus d2u by dx squared times d2u by dy squared at the point x0, y0, and we're going to be trying to find what is the value of E0 for x0, y0, and that will tell us what the character of that stationary point is. So for finding the three different types of stationary point, we have the character being greater than 0 leads to a saddle point. That's simple. And then if the character is less than 0, we'll need to use d2u by dx squared at the point x0, y0, and if that's less than 0, it's a maximum. If it's greater than 0, it's a minimum. And if E0 is equal to 0, we'd need some higher order derivatives, but we're not going to be looking at that in this case. So you're unlikely to come across those. And the proof of all these criteria is in the next section of the functions topic. So if we start with this function, u of x and y, which equals x cubed plus xy squared minus x minus yx squared minus y cubed plus y, we can simplify it as I've shown, which will come in handy later. But to start with, if we're wanting to find our stationary points, we need to find when our total differential du is equal to 0. So we need to find partial du by dx is equal to 0 and partial du by dy is equal to 0. So partial du by dx, well, that's equal to 3x squared plus y squared minus 1 minus 2xy, and we need that equal to 0. Similarly, partial du by dy is equal to 2xy minus x squared minus 3y squared plus 1, and again, that's equal to 0. If we add these equations together, we'll be left with 2x squared minus 2y squared, and that will still be equal to 0. So all other terms should cancel out, and we'll just be left with this. So that implies that therefore y is equal to plus or minus x. So in the case that y is equal to plus x, we'll have, if we sub that into either of these expressions, we'll get that 2x squared minus 1 equals 0, or 2x squared equals 1. Therefore, x is equal to plus or minus 1 over root 2, and therefore y is also plus or minus 1 over root 2, but it has to be the same value for this case. So we'll have 2 points there, and I'll write them here. We have x being plus 1 over root 2, and y being also plus 1 over root 2. Or we also have x being minus 1 over root 2, and y being also minus 1 over root 2. Now for the case that y equals minus x, again we can sub it in, and we'll see that 6x squared equals 1 this time. Therefore, we have x equaling plus or minus 1 over root 6. And so we'll have the same thing again, but this time we'll have that y is minus whatever x is. So for the first point, we have x being 1 over root 6, then y being minus 1 over root 6. And then we could finally have minus 1 over root 6 x, and y being just 1 over root 6. And I apologise that you couldn't see me writing these, but there you go. That's our 4 stationary points, and now we can find the types of each, and I'll write up a big table and then talk through it. So what I've done here is I've worked out dtu by dx squared, dtu by dy squared, and then dtu by dx dy to work out E0. So I've gone through the process of doing this calculation for each point, and then I've also worked out this for each point. In case we have E0 being less than 0, we can then differentiate between maximum and minimum. So that's what this first term is. It's to determine two maximum and minimum. This is to determine whether we have a saddle point or whether we have a maximum or minimum. And then I have the value of the function at the point. So this is representing at the point P, where P is our P1, 2, 3, and 4, which are these 4 points. And then I'll write out the types with you. We can work out which is which. So for point 1, 1 over root 2, 1 over root 2. We have E0 being positive, therefore instantly we can ignore this whole section, and we know that's going to be a saddle point. Next, again, E0 is positive, so we know that's going to be a saddle point as well. And these are both located where u is 0, so it's a height 0 above the xy plane. Now for point 3, it's negative, so therefore we do need to look at this d2u by dx squared at the point P. And in this first case, it's positive, therefore we have a minimum located at minus 2/3, square root of 2/3. Then finally, we have a negative d2u by dx squared for our negative E0, so that must be a maximum. Now, with these 4 points and knowing what type of stationary point they are, we can arm ourselves to draw this function out using contours. So we're going to be looking from the top down. So as you can see, I've drawn this function, and initially this looks quite complicated, but hopefully I'll be able to explain it. So the red section is representing where it's increasing away. So as before, this is similar to, on this point, it'll be going up like this. That's the red. And then the blue is going down. So the blue highlighted area is where it's decreasing in value of u. So for point 1, what did we find? We found it was a saddle point represented on u equaling 0, and it was at the point 1 over root 2, 1 over root 2. So it falls on this y equals x line, which is a point of contour equaling 0, and so is this x squared plus y squared lines are where the contour is 0. And I said that this would be useful, and it's because this is where u equals 0. So x equals y, and x squared plus y squared equals 1. That's the two lines or contours of 0. So our 0 point, you could say sea level, for example. So from here, we can see this is a saddle point, P1, and so is P2, and this is going up in the function like we had before, and then going down every point, going down is like that for the saddle point. So this saddle point is saying, yes, it goes up in value in these red sections, but it goes down into this blue section. Similarly, down into blue here and up into red, like that. P3 is a minimum, so it must be in a negative dip. And we find, therefore, that this contour is going down like a valley, and we have this point right at the bottom, and that's our P3, and it agrees with how we've drawn it, being that its point is positive in the x direction, negative in the y direction, so positive x, negative y, and then the opposite for point 4, which is at a peak, so it's the highest point, like a mountain, and therefore that's how we draw this function. This is just the local behaviour. It might come up here and be even higher maximum, and similarly this way, but this is what we found for how we draw this function, and using contours and therefore the highlighting to sort of help with what these contours are actually representing. So what if we wanted to find the maximum volume contained within a rectangular box, as I've drawn here, and it has a fixed surface area A? Well, we know the volume is just going to be x times y times z, and the area is going to be 2 times x times y, so we have 1 here and then a face over there. Then we have 2 times y times z, so this face here, and then 1 on the other side like that. And then finally 2 times x times z, so this top face and the bottom face. That's our surface area, and we know it's going to be fixed. In this description, x, y, and z are not independent. We have that if we changed x, for example, we'd need to change y or z accordingly to keep our surface area the same. So what we want to do is take one of these variables out of the equation, literally, and then we can work from there. So let's say we take z out of the equation. First, we need to find what z is in terms of the others, and then sub that in. So z, using our area equation, is going to be a minus 2xy divided by 2 times x plus y. We've taken this across, and then we've added these terms together, factoring out z, and then dividing by it. So what we can do here then is then sub in z into our volume equation, and we're left with v being xy times a minus 2xy divided by 2x plus y. Now, x and y are independent. If we change x or y, it doesn't affect the other. And so what we can do here is similar to what we've done before to find the point. So we'll use dv by dx, partial dv by dx, and partial dv by dy, set those equals 0, and find a point which is our stationary point. This will tell us our minimum or maximum value. I mean, we're looking for the maximum. So if you just do that working, I'll leave that as an exercise to you, you'll find that x0, our point, will be for the area A divided by 6, square rooted, and that's also equal to y0, which is also equal to z0. So therefore, our V max, our maximum volume, is just equal to a over 6 to the power of 3 over 2. And therefore, given that all these x, y, and z are equal, this is actually a cube. So a cube is the maximum volume cuboid or rectangular box for a given surface area. Today we've learnt about stationary points. This draws an end to the partial differentiation section of the functions topic. In the next section we'll be looking at series expansion. So if you want to learn more, I'll see you there. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.